This is a little video to, I think, add a little bit that the calculus book I teach out of, Stewart, does not have. He talks a little bit about moments and the center of mass in one dimension, and he first talks about the discrete case where you have basically a long, thin rod, and you have a bunch of discrete masses that are idealized as being localized at just exactly one point, and all the mass is concentrated there. And he talks about how the x coordinate of the center of mass, often called x bar, it's often used for a center or a weighted average or something, um, is just going to be the sum of what are called the moments. These are really the tendency. This measures how much tendency to turn around a fulcrum some masses give you, divided by the sum of the masses themselves. Now, this is often better understood. Let's say there's n masses, so it's going to be sum I equals 1 to n. It's just a weighted average, just in the sense of like average a grade with some things being weighted more than others. It's just a weighted average of the position coordinates of these different masses. And the weightings are literally, well, not quite literally the weights, they're the masses of these guys, although you could multiply it by the acceleration of gravity and get literal weights. So you want to think of a center of mass is the x-coordinate of a center of mass in this one-dimensional situation is the weighted average of the positions of those masses. And then I think he really misses something. So he says that. I think he really misses something by going to a two-dimensional example, like a plate that has extent in both one direction and like the x direction and the y direction. I feel like that's better left for multivariable calculus. The more direct continuous analog of what that does is I've got some sort of rod that isn't just infinitely thin and massless, and I put these discrete beads on it, but I have a rod with varying density. It's still thin, so it's essentially one-dimensional. And it's interesting because he talks about this earlier on in the book when he just talks about the idea of the mass of this whole rod. Let's say like x equals 0 is right here, just to be definite. The mass of this whole rod is the integral. Let's say this is x equals a, x equals b. It's the integral of little bits of mass. Okay, what is a little bit of mass? How would you calculate a little bit of mass of a little chunk of this guy? Well, if I happen to know that the length of that chunk is dx, and the density, let's say the density is possibly a variable function, that's where it gets interesting. Let's say d of x, and that is measured in, let's say, kilograms per meter, a linear density. Well, then the mass of this little bit is exactly just that density times dx, because this is really defined to be how much mass is in a little bit, wherever you are, divided by the length, mass per unit length. And voila, and of course it's going to be, let's say, from x to b. So he talks about this as a great example, and it is a wonderful and super important motivating example of integrals in general, that the integral of a variable density function is how you would get the mass. Well, let's look at the analog of the center of mass calculation. Just in this way, you can think of every little bit. I guess I should hatch them differently. You can think of a bunch of little bits, each with length dx, and their corresponding amount of mass dm. And this we can look at the formula for x bar, which I probably shouldn't have erased. That was the sum of mixi over, what was it? It was the sum of the little bits of mass. That's exactly the total mass. Okay, so that's going to be the integral of d of x dx. That's the total, nothing more nor less than the total mass. And then what does this become? Instead of a discrete sum of 5 or 10 or 20 masses with these discrete positions, we're going to take that sum and we're going to turn it into an integral. The analog of the mi is dm, and the xi is just the position that all the little bits are at, and the sum was going to turn into an integral. And then we just have to remember that dm is more properly calculated as d of x dx. So you really want to think of this as a direct generalization of the discrete case. This is the mass of a little bit of the rod. You're sort of sectioning it up into a bunch of little bits and just sort of pretending it's discrete. Then you have to multiply that by the position. So you're getting a weighted average of positions. You integrate that, because that's just the overgrown version of a sum. And then, of course, to make it a weighted average, you have to divide by the sum of all the weighting factors. And that's the total mass. So this is a really useful thing to calculate. And it's just based on a one-dimensional object and a varying density that says, well, some parts over here are like really light. That's where this d of x would be a very small function. Here, maybe d of x is very heavy. D of x is going to be big because it's a heavy function. It's very dense over here. And you're going to integrate that times x. And then you're going to divide it by the integral of just d of x itself to get the total mass. So again, it's just the continuous version of a weighted average of the position variable x. And that's going to be the center of mass. One reason I'm doing this is because there's a direct correspondence between this kind of calculation and an average or mean value, or what's called an expected value in probability. And that's where this would be a probability density function. And this would be the variable that you're trying to calculate the average of. And this carries over with no change into that situation as well.